Okay, so for this lesson, we're going to start off on Chapter 6. And Chapter 6 is all about functions. It's all about getting to know functions, their graphs, um, what polynomial functions are, and their behaviors. The reason why we study functions in math is because functions represent real-life situations. So lots of different things in industry and in motion and science and stuff like that. If we can express the motion of a particle or the movement of the market or how things sell and what profits are and stuff like that, those are all modeled by mathematical expressions. And the functions are called polynomial functions for most of those things. And so we're going to study behaviors. 6.1 is we're going to focus on the graphs of polynomial functions. And so, I should have did this before we started the lesson, but you're each going to need a graphing calculator to graph some of this stuff here. So why don't we just pause and hand out those calculators. All right, now that you have your calculators in front of you here, I'm going to show you how to use them if you're unfamiliar. I'm going to turn it on there. That's the on button. That's the first important thing you're going to need to know about. Up here, the y equals function right here, that gets you to this screen, which is a list of y values. So y equals this, y equals that. You can put a whole bunch of functions into the calculator at once. Y equals button right here. Y equals, you bet. All right, so one of the basic types of functions that we're going to take a look at here is something called a linear function. Now we're going to name these officially a little bit later, but this is a linear function. Can anyone guess? Here's a picture of two linear functions. Can anyone guess why we call them linear? Because they are straight lines. Very good. So straight lines are functions that have a y value, and I don't know if you guys recall or not, but this, and I'm just going to flip over to the notes because I do have somewhere. I don't know if you remember function notation, but this right here, this f of x, okay, that is the same as y. So y equals f of x. They're the same things. So you've seen this kind of stuff before, y equals x plus 1, right, as an equation of a line. This f of x is function notation, saying that this expression over here is a function, okay, of y. It's a function, y is a function of x, and we'll talk more about that later if you didn't get that. But anyways, f of x equals x plus 1 is this line right here. So maybe in your calculator, I'll get you to draw that. Make sure you can get a line that looks like this. So your variable button is right here. It's this one right here, x comma t comma theta comma n. So you just put that button and then plus 1. Okay. So you have there y equals x plus 1. That's the same as f of x equals x plus 1. Now, if you graph it, well, you shouldn't have that circle there. I guess that was me making that circle before. There's a graph button right here, yeah. In the top right, there would be a graph button. So you should have this line that extends through. Now, forget about that circle for a second. Zoom, if you put zoom 6, that gets you to a standard window size of kind of like 10 by 10 by 10 by 10, like that sort of thing. So you have the origin in the middle, and it goes out to 10, goes up to 10, back to negative 10, down to negative 10. Okay? So once again, y equals, you plug in your function there, x plus 1, and then graph, and then if you need to, zoom 6 gets you to a standard window, okay? Now we may have to adjust the window for certain functions if they don't go near the origin. If the functions don't kind of appear near the origin, we may have to adjust the window so we can see it. For now, that's that. Okay, so straight line, that's called a linear function. Linear straight line function. Okay, you might want to write that down. Straight line function. And I want you also to notice this right here, that a linear function has a degree of 1. Okay, a degree of 1. So why don't we talk about what a degree is? So when we're looking at polynomial functions, there will be functions of varying degrees. Okay, each function that's written will only be one degree, okay? It can't be multiple degrees at once. The degree of the function is, it's the largest exponent that you would see on any of the variables in the expression. So this is an x variable, right? Right here there's an x to the power of 1. There's nothing that's shown there, so we assume that to be x to the power of 1. And of course down here, there's an x term, and it has an exponent of 1 on it, so that means it's degree 1. So every degree 1 function is linear, right? And we'll see that in the textbook when we take a look at our summary, okay? We'll see all of this together. So I'm just trying to kind of explain this, so we'll see it all at once a little bit later when we talk about the review part, okay? Now, intercepts. Hope you remember what intercepts are. An x-intercept is where the graph, or the function, intercepts or crosses over, or touches at least, the x-axis. Here's the x-axis right here, this horizontal axis. So a linear function always has one x-intercept, always, and only one. It can't have more than one. And a linear function, that is, when it has a variable x here to the power of 1, will always have 1. It also always has one y-intercept, and that's where it intercepts or crosses through the y-axis. Okay? So those are two characteristics of linear functions. We should talk about end behavior. So end behavior is what we need to talk about here next, and it's explained sort of over here, although I don't really like this explanation, really, to tell you the truth. But this is in your textbooks. Let me read it, and I'll tell you what I would change. But it says the description of the shape of the graph from left to right on the coordinate plane. So I don't really like that word shape, the description of the shape. I would rather say, a description of where the graph seems to begin, which quadrant the graph seems to begin in, and which quadrant the graph seems to end in, end behavior. So the two ends of the line or the graph, sort of, where are they on the coordinate plane? So I would not use shape, probably. I would say the description of the beginning and the end of the graph. That's what I would probably like to say. The beginning and the end of the graph, or the alpha and omega of the graph, if you want to put it that way. Beginning and the end of the graph. And how we describe that, and you notice over here, we describe end behavior by stating the quadrants. So in this case, the line extends from quadrant 3 to quadrant 1. And how are the quadrants labeled? You may not remember that, but here it is down here. It's also in your textbook. On this one page that's got a lot of information, so I kind of clipped the whole page. So this over here is quadrant 1, okay? And that has positive x values and positive y values. Over here is quadrant 2. And you notice we're going to go counterclockwise here around the horn here. And so this is quadrant 3 down here, and then quadrant 4. Okay? And we usually use Roman numerals to represent the quadrants. So all right, let's take a look at the second graph here, this one right here. Okay, y, or f of x equals negative 2x minus 1. So let's go back to our graph, to our calculator there, and let's graph that one as well. So why don't you do that on the second line? Negative 2x minus 1. Now, can I just pause for a second? This is super, super important. Everyone listen. This button down here is the negative button. So on the very first term, this is not a subtraction. That's a negative. And you have to put negative there. If it's a subtraction like this between this term minus this term, then you use the minus. If you interchange those, the calculator is very particular. Okay, it'll say there's some kind of error. All right, so you want to make sure that this is a negative in the very front, and this is a minus. But if you graph that, you should see a line kind of almost forming a perfect X there. But it's sort of traveling in a downhill direction, right? Just like this one. Here's the graph drawing in your textbook. Okay, So if we take a look at the characteristics of a linear function, it still has one x-intercept somewhere around there. It still has one y-intercept somewhere around down there. But the end behavior is different, isn't it? The end behavior is different. So this particular graph kind of begins in quadrant 2 and ends in quadrant 4. So that's the end behavior for this graph. Both linear functions, but different end behavior. Now, what do you think it was that caused the end behavior to change? What's different between the two functions, and what do you think it is that changes that end behavior? What makes them slant the opposite way? So look at these two functions right here. And let me rewrite them for you. So y equals x plus 1, and we have y equals negative 2x minus 1. Does anyone remember, like from grade 10-ish, when we first started looking at this? I know some of you do. What's negative? The minus 1 here. Okay, that is different. Okay, there's plus 1 here and minus 1 here. That's not the part, though, that makes it slant the different way. This part right here is actually the y-intercept. This plus 1 right here is actually where this line crosses the y-axis. And the minus 1 down here is where it crosses the y-axis, minus 1. So what's the other part that's different? Yeah, the minus 2, or the negative 2, right? We're talking calculator language. It's negative 2, not a minus 2. So if you remember this, guys, y equals mx plus b, the slope y-intercept form. So remember that the coefficient, or the number in front of the x, that's a positive 1. This is a negative 2. That's what determines the slope. All right? And so the slope, when it's positive, it goes up from left to right, like we see this one does. Up from left to right. And a negative slope goes down from left to right. The other thing you might want to notice is that a slope of positive 1 isn't quite as steep as a slope of 2, right, or negative 2. You see how this is quite a bit steeper than this one? Yeah, maybe a little bit. Okay, so we got to try and bring back some of this knowledge that we learned a while ago. Okay, any questions about this page then? All right, let's go back to the textbook here then, and let's move on to the next page. There's another type of function we're going to talk about. That's the next one that they talk about, and it's a cubic function. All right, cubic function. Let's take a look at what a cubic function is. So we talked about a linear function, and now we're going to talk about a cubic function. Let's paste that there. Move it over maybe. A cubic function. Now, why do you think this would be called a cubic function? What about this function down here is the example that makes it cubic? The what? The 3 here, yeah. Yeah, when you have a to the power of 3, we call that cubed, right? So if you have this, that's meters cubed, right? So if you're trying to find the volume of, some kind of container here, and we have, length, width, and height, you multiply those 3 together, you get a unit that is cubed, so times itself 3 times. So you see in this one here, there is a 3 as an exponent. And not only that, it's the largest exponent on any of the variables in the terms, right? Any of the terms. So that's why we call it a cubic function. This has a degree of 3, okay? So the degree is 3 because it's the largest exponent on any of the terms, any of the variables in the terms, okay? So degree 3, cubic function. So let's get on our calculator again here. When we go back to y equals, let's clear. You hit your clear button, go down and clear that one as well. And why don't we graph this? Okay, let's graph this function right here. Get rid of that so you can see it. So 5 and then your X button. Now, you don't have a cubed kind of button here. So what do? You use this button to say to the power of, that little hat button there. That means to the power of, and then you put 3. So that's 5x cubed right there. Plus x, and then you do have a square button, and you could do to the power of 2 as well, but I'll just use the squared button. Minus 4x plus 1. All right? So double check, make sure we got that right. Looks good. Let's graph it. There we go. Okay? So on a standard window, that's what it should look like right there. Now, in a sense, the end behavior is very similar to the linear function, isn't it? It goes kind of from a quadrant here, and then it kind of goes across. Its kitty corner to the other quadrant is the end behavior. So there is a connection there. But look at the graph, it's quite different. It's not linear, is it? So cubic functions will not be linear. Let's say you want to zoom in. You can just zoom in. So we have the zoom button and then function number 2 there. You can zoom in, and then it'll ask you where do you want the center of the zoom to be, and it automatically defaults to 0, 0. So then you can hit enter again. So zoom to enter, and it should look something like this. Okay? So you can see a little bit better, what's happening there. Now let's say we want to see this top part of the graph here. What do I do if I want to see the top part of the graph? I can't see it. Make y bigger. Okay, so the y-axis is up here, and if we make the maximum, the y maximum, a little bit larger, that's right, we should be able to see that. So you're exactly right. So let's go to, now you have to do window, okay? And we're going to adjust the window. Where's y max? Okay, down here. You scroll down there. The y max is at 2.5. Let's make it 4 and see if that works. So y max of 4, perfect. Okay, that's great. All right, now we can see that little maximum point. This point right here in the graph and this point down here at the very bottom, those are called turning points. All right, they're called turning points. So back to our textbook here. Turning points. So why don't we just clip that into the notes and talk about turning points. So a turning point is defined as any point where the graph of a function changes from increasing to decreasing, or vice versa. So this graph in the example, this graph is, if we think about left to right, this is decreasing, right? This graph, it's decreasing. At this point right here, it then begins to increase. You see that? So this is a turning point. It's also sort of a bit of a minimum point in that little area, right? And up over here we have another turning point because it's increasing, and then it turns to decreasing. So here's another turning point. Now functions don't always have to have turning points. Like this one here, this curve doesn't have any turning points since it doesn't actually turn around and go back up and then back down. So you could have a graph that looks like this that really doesn't have any turning points at all. Okay? What about our function here? Let's see. It has 1, 2 turning points, right? Everyone see that? Okay. All right, questions so far? All right. So, what's the function called that is degree 2? What's this polynomial function called? Do you remember what this is called? You've had lots of experience with this one. With degree 2, who remembers what it's called? Yeah, quadratic. Very good. So this is a quadratic function. And the quadratic functions, you remember what shape they generally have, quadratic functions? a U, okay, a U, yeah, or sort of an umbrella, I guess, when they face the other way. So that shape is called a parabola. All right, that shape's called a parabola. And what we're going to do, why don't we graph this one here? So let's clear that one off. Let's see what 2x squared plus x plus 1. Let's see what that looks like. Nice. This window is perfect for that too, actually. Okay. So yeah, a bit of a U. You're right. A little bit of a U there. Okay. So you think about the end behavior for this parabola. What's the end behavior for this function? Sort of starts in quadrant what? From left to right, yeah, over here, that's quadrant 2, ends in quadrant 1. Okay? So that's the end behavior there. Notice that the quadrants are both above the x-axis that a parabola starts and ends in, so that U shape. Now, what happens if I do this to this function? If I make this term negative, what is that going to do, you think? Who remembers? It opens down. Okay, let's see. Now you have a little insert function here, so I'm going to do second function insert, so I don't have to write the thing over again. I'm going to put a negative in there. All right, let's see what happens there. Wonderful, you're right. So it opens downward. Okay, so the end behavior changes. It's important. The end behavior changes when the sign on this is called the leading coefficient here. Okay, and I don't know if you'll see this in your textbook, but it's the leading coefficient. I will refer to it. The leading coefficient is this term right here. That's the term that carries the degree of the function. It has the variable x with the largest exponent on it. And the sign here, okay, actually this, my bad. The leading coefficient is just this number. That's the leading term. So the leading coefficient is this number right there. That's the leading coefficient. And the sign determines the end behavior, so that you want to make sure you pay attention to the sign. This whole term is actually the leading term. So just get that right for you. That's the leading term, and that number is the leading coefficient. Okay, we're almost done. Questions so far, though? Any questions so far? So as we look at this chart from your textbook now, it's a bit of a summary. The one thing that we didn't talk about was this first one, the constant function. Okay, a constant function. A constant function has degree 0. So what do you think that would look like? Degree 0. Remember, the degree is the largest exponent on the variable, and it would be x in most cases, right? So if x has a degree of 0, go ahead, what does it look like? Well, okay, close. Just y equals, not x equals. But just y equals some number only. So there would be no x term in the polynomial. All right, that's what a constant is. So an example would be y equals, and what is this one? This one I'm going to tell you is a 1, 2, 3, 4. That line goes through y equals 4. That's what that function is right there. So notice there's no x term, okay, in the function. It's just y equals some number. This one is y equals, looks like negative 4. Okay? And so characteristics of constant functions, the number of x-intercepts, there are 0 x-intercepts for most constant functions. Unless we're talking about a constant function of y equals 0, that's the horizontal line that is the x-axis. In that case, every point is an x-intercept. Okay? So generally, if the line does not go through y equals 0, then it's no x-intercepts. It always has one y-intercept, always one y-intercept. And it goes from 2 to 1 or 3 to 4. So that's our constant. And we'll get to the domain and range at the very end there. All right, so we talked about a linear function. And remember, the leading coefficient, the sign of that leading coefficient tells us whether it goes up or whether it comes down. Linear. Here's quadratic, the parabolas. right? If we talk about intercepts for a parabola could have 2 intercepts, like this one. It could have 0 intercepts, like this one over here. It doesn't touch the x-axis at all. Or it could have just 1 x-intercept, where it just touches just once. Each parabola will always have 1 y-intercept. So even though this graph number 1 here doesn't look like it has a y-intercept, what you have to remember, and let me just zoom in on this real quick here. What you have to remember is that this arrow means that it goes forever upward, but also a little bit forever on to the left there. You see that? So it keeps going up and to the left. So somewhere way up high, it's going to touch the y-axis. So every function has 1 y-intercept, every function. And here's the cubic. So we can see that there's 1, 2 intercepts on this green one, 1, 2, 3 intercepts on this red one, and just 1 on this one. So anyways, this will take a little bit of work for you to work through this section, because it's a big section. But I'll just end by talking to you about domain, and this domain and range I'll have to probably come back to. Domain is all possible values for x. Okay, so it's all the x values that are allowed. And for all of these, when you see this right here, that means that there are no restrictions. X can be any real number. That's what that R means, any real number. The range is the possible y values. So if you look at this parabola, for this blue one, the range goes from this y value up. That's it. There's nothing below that. For this parabola, it's this y value up. For this one, it's this y value of 0 and down. See that? So the range can vary a little bit. Just remember that domain is all possible values for x, and the range is all possible values for y. Alright, so that's enough, I think, for the teaching on this lesson for now. I'll give you your assignment. So you just take a look at that review for a sec.